So till date, in a number of previous classes, we have basically discussed about various types of improvement on the pipelining. So if we do a very brief about what we have done till date, is we are actually dealing with some single case stage instruction pipelining, where we have some properties for those pipelines that we have used. For example, all the instructions regardless of type traverse through the same set of pipeline stages. That means we have fixed some particular set of stages, and we have assumed that all the instructions that traverse, that executes, actually traverse through the same set of stages in some order. Now if we do in this way, that means obviously uh, there we will see some limitation that can arise due to this scenario. But before that, let me complete the properties that we have seen about the pipeline. For example, at considering point number 2, at most one instruction can be resident in each pipeline stage at any time. That means we have seen that if there is n number of stage in a particular pipelining, we have seen that in an ideal situation, that means if we consider there is no um, stalling or no hazard, then each and every stage will be busy with at most one instruction at a time, and that means the output that we will get from the pipeline is one instruction per clock cycle. So this is actually sometimes we uh, express by a specific unit, and that is what we call CPI, that is cycles per instruction. So that means we know that at most one cycle is used to execute one instruction at a time in an ideal scenario. And then the third point is the instructions advance through the pipeline stages in a lockstep fashion. You know what this lockstep fashion means? It means that since we have seen that each and every instructions are executed in the pipelining one by one in different stages. So because of some unavoidable circumstances, if it happens that one instruction somehow become busy with a particular stage for more than one clock cycle, then all the following instructions, all the instruction that is following that instruction become stop and cannot go further, and that basically decreases the efficiency of the pipelining that we have seen. So in order to improve the efficiency of the pipelining, somehow we should overcome all these problems that is generated because of these three properties. So if we list all the limitations that we have found regarding all the different type of pipelining that we have seen in previous classes, can be written in these 3 points. The point number 1, the maximum throughput for a scalar pipeline is bounded by one instruction per cycle. And this is just I told you that since each and every instructions are using one stage at a time, that means if we forget about any hazard, then also that means in an ideal scenario we will get only one instruction out from the pipelining in per clock cycle. So somehow if I want to increase the throughput, in this ideal scenario the throughput is actually 1 or maybe less than 1. if there is some hazard. Now if I want to increase this throughput, somehow we have to modify the pipeline in somehow. So how we can modify, we will see it very soon. Second point is the unification of all the instruction types into one pipeline can yield an inefficient design. I mean, there are different type of instruction present in a computer system, right? Some instructions are branch instructions, some are floating point instructions, some are ALU instructions, some are memory reference instructions, and many more. And we can understand that each and every instruction should not need all the stages of the pipelining for their execution. For example, if you are able to calculate the branch target address in the decode stage, then branch instruction should not use the execution and the other write back stages. But the problem is that due to this unification of all the instruction type in one pipelining, it's not possible to use that other stages which is not usable by the branch instruction at the same time by the trailing instructions, which basically degrades or may degrade the performance of the pipelining. So this is another limitation we can consider. And the third one is the stalling of a lockstep or rigid scalar pipeline induces unnecessary pipeline bubbles, because we know that due to some unavailability of instruction or unavailability of data, we have seen that it may happen, or it may be due to the increased length of some instructions. We have seen that a particular stage is become busy with some particular instructions, and some other stages remain blank in the sense they are not at that time busy with some instructions because the leading instruction cannot proceed further because of the hazard. So all the trailing instructions remain stopped in the previous stages, which creates bubble within the pipeline, which is definitely degrades the performance or the throughput of the pipeline. So as a designer or as a computer engineer, during improvement of the pipeline, we should look into all these limitations, and we have to find out how we can modify the pipeline in such a way that we can remove all these dependencies. So if we think about the improvement of the pipeline, that means it's very natural that we have to go for some advanced pipeline. Now how this advancement can be done and what are the difficulties that can arise, that we will see in this class. So we will start with the first advancement of the pipelining that we call superpipelining. The idea is that first of all, let me clarify what superpipelining is. Superpipelining is based on dividing the stages into several sub stages and thus increasing the number of instructions which are handled by the pipelining at that time. So if we elaborate this point, what I mean that instead of considering fetch, execute, decode each and individual stages, if we are able to make more division among all these different stages. Suppose that the fetch operation can be divided into two parts, first part of the fetch operation and the second part, and same thing for decode and execute and write back also. That means what I can say, that we will able to divide the stages into more sub stages, maybe two or maybe more than two, and according to that we can increase the number of instructions which can be handled at the pipelining, because those sub stages are actually now considered as the stages of that advanced pipelining. For example, in this particular design, if you see that we have a pipelining where I have say 5 instructions present over here, which we want to insert within the pipelining. And what we have done, we have seen that suppose this is the total fetch stage that we had in a normal scalar pipelining we have encountered till date. This is fetch, then the this is decode, then this is execute. I mean, sorry, not decode, actually it's a 5 stage pipelining, so you can consider that it's a instruction fetch, then instruction decode, then operand fetch or operand read, then execute, and then write back. So these 5 operations can be there. And somehow, if you are able to divide those fetch, decode, execute, operand fetch, all the stages into more part internally, then logically we can think that each and every stage is basically divided into 2 parts, so that we have expressed by this dotted line. And if we are able to do this for all the instructions, then naturally the time in case of the instruction 2, that I don't need to start instruction 2 after completion of the whole fetch operation of instruction 1. Rather, after completion of the first phase of the fetch 1, I can start fetching of instruction 2. So basically what we are doing, we are actually, you can say, increasing the depth of the pipeline, right? As we increase the depth of the pipeline, so that means what I can say, in previous case when we had not we had no idea about division of this fetch, execute, write back, and decode stages, then if we have a 5 stage pipelining, we can say that a particular instruction will be busy with one of these 4 stages, the next instruction will be busy with the next stage, and next to next, and so on. So at a particular time, there will be 5 instructions running within the pipelining in a normal scenario. Forget about the super pipelining. Forget that there is a arrow. I mean, there is a dotted line in a particular stage. Okay, so we have 5 stages right now. If we have, then I can say that at a time, 5 instructions can run in the pipelining in different stages, right? But when we will able to divide each and every stage into 2 substages, then naturally it will, the total number of division or the substage that we'll have in the pipelining become 10. So basically we are increasing the depth of the pipelining. And if we increase the depth of the pipelining, naturally at that time the total number of instructions that can run parallelly within the pipeline will become 10. Although throughput will be only 1, that is another issue. But what I can do, I can start the instructions more quickly than previous cases. So this is one advancement from the from I mean from the time point of view. So that means basically what we are doing, we are actually trying to use the one clock cycle for 2 instructions. So, or in other words, you can say that our instruction can be completed now t by 2 clock cycles, if we consider t is some amount of time with respect to the clock cycle. And that is what actually given over here, the task that requires less than half a clock cycle. But and obviously we'll have this two ideal scenario we have to consider, that is tasks that require less than half a clock cycle, and second ideal scenario can be the no duplication of hardware is needed for these stages, because fetch is a single stage, but ultimately it will can be logically converted into 2 parts. That's the idea. Now, obviously, if we increase the depth of the pipelining, we will encounter some set of limitations. For example, first thing, if we compare the performance, if we see the performance of this super pipelining, we will see that with respect to, if we consider the advantage of this, I can say that by dividing the each stage into 2 or more substages, the clock cycle period t, whatever whatever unit you can take, can be reduced into t by 2, right? So it will basically produce twice amount of instruction at a particular time span over the previous normal scalar pipelining. But there will be some um, you know there will be some disadvantage also. For example, in point number 2 I have given that for a given architecture and the corresponding instruction set, there is an optimal number of pipeline stages. Increasing the number of stages over these limits reduce the performance. How? Because as we have seen that there, because of some dependency, if we just I mean, uh, just delete the, if we remove the ideal scenario, because in a practical scenario, definitely the ideal assumption will not hold. At that point of time, I can say that if there is some stalling or some, amount of unavailability of instruction or data in that more depth pipelining, so naturally the number of instructions that will become in a suspended state will be more than previous cases. So naturally it will produce more stalls and a lot of bubbles will be created, which will degrade the performance of the pipelining. So basically we have to think about how, keeping, we want to increase the speed of the, processing, but we cannot compromise this, this bubble or stalling, this type of limitation. So how we can, keeping all this practical scenario in mind, how we can improve the pipelining, that is the question. And as an answer, we can say we can go for another more advanced pipelining over the super pipelining, that is what we call actually superscalar architecture or superscalar pipelining. So naturally question will come, what is superscalar pipelining? So you see, before understanding what superscalar pipelining is, let's start with what we have seen from the very beginning. From the beginning of our architecture, class that we have started. We started with a, non-pipelining scenario. Non-pipelining scenario means that we have a processing unit which I have not divided into a number of stages. So we have seen that there is only one processing unit which is not even parallel. There is no parallelism in this particular instruction, a particular hardware. That means one instruction will come in the unit, it will come out from the unit, and then the next instruction will come. And we have seen that it's basically, the number of time that requires to complete, in this scenario will be huge, and that's why basically we introduce the concept of parallelism in this way. What we have done, we have divided that amount, that particular hardware into a number of independent stages, so that each and every stage can be busy with different instructions at same point of time. So naturally what will happen, at a time, what we have seen from this diagram, I can say that at a time there will be 4 instructions running in different stage in the pipelining, which basically can be considered as a temporal parallelism. Temporal in the sense with respect to time, because we are sharing the same time for different instruction into different stages. But we have seen that there will be some set of stalling and some bubble will be there, and different type of limitation can be arised. And if we want to, you know resolve this dependency, I can say that I can improve in a different way also. That I can do, what I have done over here in a another type of improvement, that we have not divided a particular, the whole hardware into 4 different stages. Rather, we have replicated the same hardware into 4 times. So what happened, that each and every hardware is basically a non-pipelined hardware. Okay. So but since they are replicated more than once, for example 4 times here, that means at a time 4 instructions can run in these 4 different stages. So this is actually what we can say, that spatial parallelism. So basically, you can say that obviously, with respect to time, we are not dividing a particular hardware into n number of stages, but we are actually trying to run more than one instruction at a time in some particular situation. Maybe one instruction will be in fetch, one instruction will be in decode date situation, one instruction in some execution situation, and so on. And you see that ultimately it all the instructions are in all the instructions running on these different stages are independent to each other. That is fine, but problem is that it increases the hardware complexity a lot, because a particular hardware has been replicated many times in that particular system. So in order to deal with the problem that we find in temporal parallelism as well as in spatial parallelism, what we can do, we can make a mixture of this temporal and spatial parallelism to get more advanced pipelining, doing something like this, what we call basically parallel pipeline. And in case of parallel pipeline means we are actually replicating the hardware more than once, and each and every hardware we are keeping a temporal parallelism in between them. I mean that each and you see, I hope from this diagram you can easily understand that we have replicated the same hardware twice in that system, but each and every hardware have a temporal parallelism. So with respect to the hardware complexity point of view, definitely this is more complex scenario, because we have a replication of different same stages more than once. But with respect to the processing time, if we consider, then we can say that we can run more than more program than normal temporal parallelism over here in case of in a parallel pipelining. Because in a temporal parallelism we have seen maximum, according to this diagram, maximum 4 instruction can run at a time in some stages, but here it can be doubled, it can be 8, because the same hardware has been replicated twice. So now if we go for some example, real life example that some people use in practical life. For example, let's come to this 5-stage I-486 scalar pipelining, which is basically a normal scalar pipelining that we generally discuss, we generally think about till date, that it has 5 different stages, instruction fetch and decode has been divided into 2 parts, decode 1 and decode 2, then execution and then write back. That's all. Now obviously you know that what is the limitation of this, because we know what is limitation of a normal temporal parallelism. And that's why what advanced pipelining has done, for example 5-stage Pentium parallel pipelining, what has done, it has divided each and every stages into not each and every stage, actually it has actually increased the depth of the stages, so that more than one instruction can run at a point of at a time in a particular stage. For example, here it is 2. So at a time you can fetch 2 instructions, and you can continue with this for decode, and after decoding either you will go for U pipe or V pipe, that may depends upon the instruction type, and then it can go in decode in this side or in this side. But ultimately you will see that the total number of fetching is running twice over here, total number of decoding is happening maybe obviously twice than the I-486, and similar thing for decode to write execution and write back also. So this is an example of a parallel pipelining. Now you see that if we think about if we try to think for a solution of the point number 2 that we had, for example this one, you see this unification of all the instruction types into one pipelining can yield inefficient design. This is what we have discussed, that each and every instruction does not require all the stages. Now which particular stage will be used in practical scenario, which pipeline stage will be used, that sometimes most of the times actually depends upon the type of the instructions, because some instruction can be ALU instruction, some instruction can be memory reference instruction, some can be floating point instruction, and so on. So to get the get out from this unification limitation, we can go for a diversified pipeline. But before that, I mean, we can observe one thing, that we can that speed up that we know that represents the throughput, or the not throughput of a pipelining. For a scalar pipelining, we can define the speed of in terms of depth of the pipelining, right? Depth of the pipelining means the total number of stages that we have in the pipelining. But in case of speed up for a parallel pipelining is determined by width as well as depth of the pipelining, because the same pipelining has been replicated maybe more than once. Anyway, so if we go for the solution for the unification problem in a pipelining, we can go for a divert, that is basically what we call diversified pipelining, where we have seen that, you see, unlike previous cases over here, in case of like 5-stage Pentium parallel pipelining, we have seen that instruction fetch, decode, execute all have more than one places, so that, I mean, more than one instruction can be fetched or decoded or executed at a time. So this particular property, his property holds in the diversified pipeline also, up to the read operand part. So this part, I have a 5-stage pipelining here again. So instruction fetch, instruction decode, then read the data, that is that means the operand fetch, and then execute and then write back. Now up to the operand fetch, there is no specific difference in different type of instructions. The instruction type may, I mean, actually differs with respect to their execution. That is why you see in the instruction fetch, up to the read read data phase, we have the stages, the stages are actually drawn in this way. I mean, what I mean that each and every stage is having depth 3. So at a time 3 instruction can be fetched, then 3 instruction can be decoded, then the 3 the 3 data for those 3 instruction can be stored. And after this, depends on the instruction type, whether this is a ALU type instruction or a memory reference instruction, the pipeline decides that which particular stages should be used for that particular instruction, and depends on that, from this RD phase there is a diverse option, or there is a diverse option to go from either this side or this side or this side or this side. Okay, and then after completion of the execution in this part, maybe instruction 1 will go through this ALU side, instruction 2 will go instruction 2 say is a floating point instruction, so instruction 2 will fetch, then decode, then operand will be fetched, then it will go for this floating point part. Instruction 3 may be memory reference instruction, instruction 3 then will come in this side, and ultimately after completion the execution in different units, depends on the instruction type, they are again they are again came together and stored in the write back stage, just in the same way as we have in the previous cases, and then it's written back in the register parallelly. The result can be stored parallelly. But so that means you see, I mean, we can have more. So this is for this is basically solving the the limitation that we have pointed in point number 2. Now if we go for the third limitation, that is, let's come back to the third limitation again. We will see that the stalling or of a lockstep or rigid scalar pipelining induces unnecessary pipeline bubbles. Now this is because actually it happens that, suppose there is some instruction, there is a lot of, I mean, some set of instruction running in a pipelining, and sometimes it happens that there are some instructions which are independent to the other instructions in that program. So naturally it's better, it is always best that if we are able to pass those uh, independent instructions if the some phases, some stage is free at that point of time. But since we have the instructions are executed in normal scalar pipelining in a lockstep fashion, that means instruction 1 will pass, then only instruction 2 will come, then only instruction 3 will come, whatever the stage doesn't matter. But it's not like instruction 3 can basically overtake the execution or decode of instruction 1. It's not possible. That's why ultimately there will be always a chance of creating a bubble, and this is what we can remove with the help of what we call superscalar pipelining. So how we can do this, let's see. So before we understand that, so we'll start with this concept of dynamic pipelining. So we have seen that we have some stages. Stage I is executing with one instruction, then it will be stored over here and then it will come here. So it's basically what, that's why it is called single entry buffer. Now if we want to make a parallel pipelining, we will see that we will have in a particular stage we will have more than one instructions. So all the instructions will be fetched and then they will get stored for some time to be executed or maybe to be executed in the next stage. Okay, and the order that in previous stage we had about in the pipelining should be maintained, right? So that we have seen. So that's why, this particular situation we can say that it's a multi-entry buffer. That means in this particular buffer we have more than one instruction we can store, but ultimately still the problem is not solved. That is the problem of the lockstep fashion. So what we can do over here, you see, we can say that okay, let's have more than one stages over here in parallel. Okay, so n number of stages here over here which are coming in some particular order. Now when they will get stored on the buffer, you see I have given that buffer entry should be more than or equal to n. What I mean to say is that it's not possible that when you will pass the instructions from the previous stages, all the instructions are independent to each other. It is not possible. There will be some instructions which are independent, there will be some instructions which are dependent to previous instruction, or which depends on or based on or some instruction on which some next instruction depends. It may happen. So that means depends on the type of instruction, type of in the sense whether the instruction is an independent instruction or a dependent instructions. Some instructions will come to the next stage, and some instruction will retain within this buffer because of the dependency. That is why it may happen that there will be more than n instructions that I require to store at any point of time in this buffer. That's why the buffer length should be greater than n. And the problem is that we will face here is that ultimately what we will see, that suppose we have I1 to I10, total 10 instructions present in a program, and in I1 to I10 there will be say 3 or 4 instructions which are independent. So what will happen, those independent instructions will be executed first without actually without depending any execution of the other instructions. So naturally, if we consider the order of the execution of the instructions, we will see that the order of the execution of the instruction in the previous stage was in particular order, but order of execution of the instruction in the next stage will become out of order. Out of order in the sense that the exact order that we had in the previous stage will not be maintained over here, because some instruction was independent, and that's why they have executed first. So that the stage, some stage which are basically free because of some stalling or bubble, those stages can be used for the independent instructions. But still, this particular situation, actually what we can say, that it's a multi-entry buffer with reordering. So now if we make a combination of all this previous concept, we will basically find what we call superscalar pipelining. You see over here in the superscalar pipelining, what we have done, we have a situation something like this. This particular diagram you have seen in the diversified pipeline also, but in case of diversified pipeline, we have not thought about this order. We have not thought about out of order instructions. But in case of superscalar pipelining, it is basically capable to you know work with the instruction that may be in out of order. For example, what may happen over here, say instruction fetch, decode and read the data. These three does not require any out of order instructions, because instruction dependency does not depends over here. The instruction dependency mostly important in this execution stage, because maybe the floating point instructions will take much more time than the LU instructions, or maybe the branch instruction will take lesser time than the memory reference instructions, and so on. So naturally, if some instructions is completed its execution in some of the stages, then naturally somehow I should allow that instructions to store over here. So ultimately, in this recorder buffer, what's happened? In this recorder buffer, all the instructions that are coming is not in the same order that it was actually dispatched from this read data buffer, from this dispatch buffer, right? So basically, the order that I will get, the order of the instructions that I will get in the reorder buffer is basically in out of order, and it is the job of the reorder buffer is to reorder them properly, so that ultimately when the result will get stored in different memory locations, they are stored according to the order of the program. Okay, and obviously, after reordering those output of different instructions, if if they are independent instructions, they will directly go to the write back stage and will be written back in the result will written back in some memory location. But if those instructions which were dependent, first they will be reordered properly as per the program, and then those results will get stored in some memory location through this write back stage. So as a result, what we can say, that the superscalar pipelining looks something like this, that we have a fetch unit. After fetching, it's not only one unit, remember. Okay, I have more than one unit, that's why it's given a large length, so a large depth actually. So we have an n number of fetch operations can possible over here, and after this it will get stored in the buffer. And we all know that in between two different stages we have some buffer to store the output of the previous stage temporarily, and that's why we have this buffer, and we have more than one buffer here, so that I can store that amount of instruction which can be fetched parallelly over here, and then they are decoded as it is. As usual, the output of the decoding will get stored in the dispatch buffer, and it will now get dispatched to different execution unit through the reservation station. And it is the reservation station is basically a specific architecture, specific, you can say, a circuit that basically issues different instructions to different execution unit. Okay, so this different execution unit will busy with all the instructions at a time with different with different time. And after this, what happened? After this, the instructions output that I will get over here will definitely not in a particular order. Some instruction will come earlier, some instruction will come in late, but the order while writing the output of the instruction should be in that particular order. So whatever instruction while dispatching was in a particular order, and when we are getting the result of the instruction with the it will be in out of order instruction, and this out of order instructions is reordered over here, and then it's basically does the reordering, and then basically it stores in the memory location. So this is all about a basic idea of uh, mm, uh, architecture of a scalar pipelining. So we have not yet um considered the hazard and any other critical situations uh, in the superscalar pipeline. We have just for understanding the concept, we have considered ideal scenario in a superscalar pipelining. Now if some hazard happen, I mean due to some unavailability of data or unavailability of instruction, then also this particular superscalar architecture is capable to handle that, because we have different execution unit and we have a place where I can reorder the results. So in this way actually that means basically there is three part. You see, we can see the one, this part is in order. I mean its parts means actually with respect to the order of the instructions. So up to the reservation station the instructions are in particular order, then after completion of the execution it will be in out of order, and then again after this reordering the instructions in the reorder buffer, it will be in the same order as it was dispatched in the previous stages. So in this way basically your superscalar pipelining works. Now we have more advanced pipelining. We can have more advanced pipelining, for example VLIW, that is very large. I cannot remember the full form right now. Anyway, one is VLIW, and there is another two advanced pipelining we have, that is um, array processor and a vector processor. So we will look into those different advancement, more advanced pipelining in the other classes. Thank you.